the phone back up. I don't want any cops busting in. Okay, so here's our sample problem. So we have M. So M, forget that one. M equals 10 kilograms. F, I like to call it F1, I like to give it a name, is 40 newtons, is that right? 45 newtons. Mu sub S is 0.70 or 0.7, and mu sub K is 0.10. Okay, was there anything else numerical wise? Nope. So we got a sketch, we got a mass, we got a force, we've got an M, and life is good, right? Right? Okay. Well, on my sketch, I'm going to play around. Are there any other forces that I could show that were not specified? Which way is friction going? Can you determine that? Yeah, because if there were no friction, it moved to the right. Excellent. You got to think that one through a little bit. Force of friction. What kind of friction? We have no idea. It's a logic train for friction we got to go through. But it's static first. If exceeded, then it's kinetic. Okay. Now what do I do? Free frickin' body diagram, right? So I'm going to take my F1 and move it to the right-hand side to reflect that, I like the forces to begin on the mass. We have F sub G, we have F sub N, and we have F sub F. Any other forces acting on it? Notice a variant of this problem is to have F1 at an angle, either down or up, which would have an effect on the y as well as the x, right? We'd have to do components. Yes? Always think components, yeah? Well, which way do you think might be a reasonable way to assume it's moving or accelerating? Yep. So what does that suggest about my coordinate system? Normal xy. You mean horizontal and vertical? You have to do one of those things, right? Yeah. Smaller. I couldn't get away with it. Okay. What's the physics here, folks? F vector equals ma. So what does that mean? In the I direction, we have what? F1, all of it, positive. I have force of friction, all of it, negative, equals M, and I put in a positive A. Yum, yum? Okay, so I get F1 minus force of friction equals MA. Okay, that's as far as I can take that one. What else can I use? J direction, thank you so much. What do we have in the J direction? Fn, all of it, up. Fg, all of it, negative. What do I keep saying all of it? Why do I keep putting the 1 there? Yeah, it's a placeholder in case I have a sine or a cosine. That's all. I mean, you don't have to put a 1 there. But by golly, if something appears in components, you darn well better not forget each of them. Okay, anything else? So that's M A sub Y, which is 0. Yep. So this says F sub N equals F sub G equals mg. Okay. So I have 2 unknowns, right? I don't know A and I don't know the force of friction. I've used up that second equation. It told me the normal force. What do I need to do? What do we have to think about now? Not quite. Not quite. What else? What other relationship am I going to have to use? Yeah, so I'm going to write that down in all its blood and gory guts. Well, what is mu sub s f sub n? That's going to be 0.70 times 10 times roughly 10, which is going to be what? About 70-ish, right? So that's bigger than 45. So it accelerates to the left with a net force of 25 newtons, right? Wrong. Ah, exactly. So F1 is less than or equal to, how do I say this? It's less than, forget the equal part. It's less than force of friction static maximum, right? So that tells us what? A equals 0. Remains at rest. And what else does it tell me? Yeah, F1 minus force of friction equals 0 says F1 equals force of friction. So force of friction is 45 newtons. Yeah? Not 70, 45. Remember, static force of friction is as large as it needs to be up to the limit. In this case, we were below the limit. There are no steps that I could have gotten rid of to achieve this answer. I had to think through each one. Yeah?
For the friction equation,
Yes, sir.
would it be 0.7 times 10 times 9.8?
Oh, yes, but it's about 70 newtons. It's a lot bigger than 45. You're quite correct. Yeah. Let me put a tilde there just to indicate it is an approximation, but it is bigger than 45. Yum yum? So friction is as big as it needs to be to keep it at rest, if it's static. So, let's review. There it is. But for the quizzes, I might add up to more than whatever 50 points. So you can get a bonus amount to make up some other quizzes. Or to get above 70, right? So I'm going to do that from now on. And you're going to have more quizzes than popsicles at a birthday party, okay, or a pool party. Okay, so we have a couple of things remaining. We have circular motion, fluids, and energy conservation. That's a lot to cover. How much energy would be on the test? I'll be able to tell you on the Monday before the test. Okay? Because I think our test is on a Wednesday, perhaps? Scheduled for Wednesday? Is that right? Friday. Okay. It's a Friday. Okay, good. So again, it may be fluid a day or two. I put it on a Friday so I could grade over the weekend. Okay, so circular motion. What are we doing here? Are we expanding the realm of physics? No. We're just reminding what you already know. F equals ma. If something's going in a circle, A, if there's no change in speed, A is equal to V squared over R. Direction's changing. Centripetal acceleration. Yum yum? Had that on the last test. Remember the components, you had tangential and centripetal. So, okay, that's chapter 6. Let's move on to chapter 14. Let's work a couple of them. Okay, you know what that is? You've swung things run in circles, the shepherd, David and Goliath, wet towels. Yeah. So there has to be a force which provides that acceleration, and so we can draw diagrams. Now, a conical pendulum is a situation where the string that holds the ball or object is fixed, and the problem in detail, hitting the highlights. So as I suggested to you, always label your center. So when you look at the free body diagram, what have they done to the tension? How do they get this? That arises from what? Components. Yeah. I would prefer that you keep the vector on the diagram and do components separately. Components take up a lot more space, can get a lot more confusing. I want you to have that component issue resolved based upon only looking at the vector. Okay? Now, another thing you should realize here is you've got L, theta, and R. So different problems give you different things, but R can be written as L sine theta. Okay? That's where this comes from in the final answer. That's R. So we're going to solve for the speed at which the bob is moving so that it circumscribes a circle of radius R with the string tension F sub t at the angle theta relative to the vertical. So what's missing from this free body diagram? Excellent. Right. And technically, the axes are missing. So now we know what to write, don't we? Fy. This is not physics. If you can show me the law of physics that says t cosine theta equals mg, I'll give you full credit. What should you always write to get full credit? F sub y is what? Plus t cosine theta minus mg equals ma sub y equals 0. I know that it is sometimes very straightforward to know what that value is, but show me, okay? Because again, otherwise it appears as magic. What would you write in the x direction? What are the forces in the x direction? There is only f of t sine theta. There are no horizontal forces other than that. So that in this point is going to be positive, right? It's going to the right, and that's equal to positive ma. So this problem is worked by finding out what f sub t is, substitution and solving, right? Because, there's one more thing we have to do. For ma, we have to write m v squared over r, because it's a centripetal motion. Questions on that? Yum? Again, I'm going to be pretty nitpicky, as you probably have noticed. Physics, applied, then algebra. Algebra doesn't go before any of the other two. Again, normal force equals mg, not always. So you better write down F sub n minus mg equals 0 if that's the case. Okay, enough nagging. Moving in a horizontal circle. Is it ever possible to have a conical pendulum that is perfectly horizontal? You can get close to the horizontal, but you can never have perfectly horizontal because there's always the force of gravity. So there always has to be a vertical component of the tension. Oh, that'd be cool, but what would horizontal mean? Yeah, I like that. I like that. Yeah, that would be a good case. It could be right. I like that. Totally within the plane. Good. Um, how about a vertical circle? Now that gets a little bit more interesting because what changes? Well, notice if you are going, say, like a motorcycle at the circus, if you're going on the inside of that hoop, what pushes you to the center? Sometimes gravity does, but what is always acting on you? Acceleration is not a force. It's related. Acceleration is going to be there, though. There has to be a normal force. A normal force, right? Pushing you away. Okay? But what would happen if I had my good old string and I was moving it? There's no normal force there. What provides the force that keeps it going in a circle? Tension. And lastly, suppose I go over a speed bump at entirely inappropriate speeds. What's the direction of the force? Yeah, gravity is what keeps you on the road. Yeah? But the road keeps you from falling down to the center of the earth. So you see, the free body diagram, when drawn properly, makes these situations clearer. Because there's all sorts of funky ways I could ask you these questions. Yes, sir.
Are you saying there's tension when the motorcycle drives?
No. This, I mean, that would be rather cruel to have her attached to a chain or something. So this would be a normal force contact between her and the track. Precisely. Precisely. So let's do an example of, okay, something going in a circle. Horizontal. So you're going in a circle like that. Where's the center of the circle? Here, here, right there. Yeah? So when I look at it from the side, again, here's your roadway. When I look at it from the side, where is the center? It is there. So you can, based upon what we just did with friction, you can see that friction is what's giving us the force that results in the circular motion. It's the only horizontal force there is. And it's going to be limited by static friction, which is bigger than kinetic friction. And it's going to be determined in part by the normal force. Static friction acts along the radius, but it's a force. Sure. Radius is the distance. Yeah. So we're going to get that F sub F static equals mv squared over r. What do they teach you, or what do your parents teach you as their fingernails are digging into the dashboard? They teach you never brake within a curve with the car. Don't slow down in the curve. If you're going too fast, do not slow down. Why is that? Really? Okay, maybe somebody like you, okay, whatever. You probably never went, you're probably up AWOL, okay? If I look at this from above, and there's the center, yeah? And you're driving at the maximum speed for the force of friction, static, and you're saying to yourself, gosh, I'm going really fast. I think my tires are about ready to slip. What might you be tempted to do? Hit the brakes, because that's going to do what? It's going to slow me down, right? So I'm going to have A sub C that way, and I'm going to have A sub T that way if we're headed, you don't hit the gas, if we're headed clockwise. Do you agree with that? Here's the problem. The total A, total acceleration, is the vector sum of those two. So what have you just done? By hitting the brakes, what have you just told friction? You've got to have two components now. And friction says, I can deal with that, but where's there a problem? Right. How do you get friction to have a component that's not radial? If it's at its limit and it's barely holding you in that circular path, if you hit the brakes, friction will give up. It'll slide. Friction is not a maximum in each direction. Friction has a maximum magnitude. So by hitting the brakes, you're telling part of friction to slow you, to slow the car. But that reduces how much friction can be applied towards the center. So you skid. So they always say, slow down before you get to the curb. Now, some of us didn't pass the course by very much. So I'll tell you from my personal experience, what I do is I just let off the gas. By letting off the gas, I do a couple of things. A, I'm sort of like Star Trek. I'm diverting all power to the impulse engines. I'm diverting all my friction to the center. And I'm going to let the drag of the engine, which is still related to friction, the drag of the engine slow the car. Yeah. I think it'll be like braking, yeah, because you're changing the rate at which the tire's rotating. So that's related to the speed. Yeah. Good point. Yum yum. So this is sort of the trick that cops and other people do if they want to go 180, is they throw themselves into a tight turn while hitting the brakes. It makes the rear end scoot around. One summer when I was involved with the police department in a positive way, in Stamford, Connecticut, I noticed outside the headquarters that were like 4 or 5 cars that were wrinkled up pretty well. They were going to get fixed. And so the guy I was with, the cop I was with, says, hey, notice all those cars over there? I said, yeah, y'all really can't drive well, can you? And he said, no, new tire contract. The city bids out, like most cities do, for the tires in a certain period of time for each year. So they're going to buy it from one person. Well, if you issue the contract to someone else, or you change the tire model, it's like driving in NASCAR with a total different tire. It changes when you're going at the limit, it really changes what you can get away with as far as coefficients of friction being different. So the people were having a little bit of a problem getting the 180s right without having bad things happen. So, okay. So let's look at the case, which is kind of amusing here. I've always thought this to be kind of funny. This is the bank curve. How does it look different from that? What's the difference? Not a flipping difference. They got the wrong diagram. A banked curve would be like this. Okay? So the angle of banking, theta, comes into play. Now, why is there theta? Well, because we have components. Well, why do we have components? Because it's going in a circle. Where is the center of its circle? It's still where it was before. You're going around in a circular track, it's still towards the center. So what is the benefit then of having static friction? You're actually reducing it, aren't you? Yeah, good for you. So the force of friction static goes down the plane. So only a component, a cosine theta, acts towards the center. But the beauty is F sub n also will now have a horizontal component. And that, I guess, will be sine theta. So now friction has a limit, but normal forces generally do not. So by tilting the road more and more and more for a given turn, you're able to get around the curve at the same speed throughout. So the tilting would be a maximum here and here, and it'd be pretty small there. You wouldn't need it if the radius is really large. But with those tight turns where the radius of curvature is small, you have to have a lot of banking. You really become aware of that if you've ever been bicycling out on country roads. You really become aware of it. Because you'll go through some country roads where the banking is such that your head is below the outer lane. And you're like, I never noticed that. Why is that? It's the same reason that a bicycle is dynamically stable. You can lean into the turns. So the idea for a banked track, whether it's a car or a bicycle, right, is to have the normal force be directed perpendicular to the surface. And of course it should be perpendicular to the surface, duh. But the idea is to have what? If you look at a bicycle person, there's the pivot. We've got F sub G, right? And we've got F sub N, and we've got what? A sub C. Yeah? So if I can get F sub G and A sub C to be F sub N, do you see how those two add up to F sub N? We multiply by M to get MAC. If I can lean over so the normal force goes over the vector sum of gravity and the component, or I guess the centripetal acceleration, then when I'm taking a turn, it feels normal. I feel a little bit heavier, but I don't feel a desire to twist side by side. On the other hand, if you take a turn and you don't lean into the turn, which happens sometimes when you have a passenger behind you who's not really paying attention, it gets really dangerous. If you don't tilt and you apply a friction force, what's going to happen? You're going to fall over to the outside. You've got to lean into the turn. And you can take that to the extremes of motocross, right? Where the person's knee is doing like that. Motorcycle racing, I mean, they're right at the ground. Those tires must be made of super rubber or something. But they are virtually as horizontal, as low as they can go without removing their legs in a very painful way. Same thing is true for your car. So by using this diagram, we can solve for the rated speed of a given angle of banking. Okay, we want the total of the gravity force and m times the acceleration force to be along the normal. That way, when you go around the curve, like out in the country, at the rated speed, you don't notice a force pulling you outwards or inwards. You just feel a little bit heavier. That makes sense? Well, it's time for me to come back here and find some space. Or not. Now that we're talking about forces, it's time for us to come back and discuss the difference between centripetal and centrifugal. When you're moving in a circle, you have a force towards the center that produces the centripetal acceleration. What force produces the centripetal acceleration? Any flipping force in the catalog, right? It's a force. It's an acceleration. F equals ma. Next question. It can be friction, strings, small chipmunks, very bad attitudes. Anything, any force can make something go in a circle. But there is a fictitious experience that you have. When you're in the front seat of an old-fashioned car that had what we call bench seats, not buckets, but it was a just continuous bench, like at the park, made of vinyl, some other popular synthetic surface. It was not fiber. Fiber has more friction. See? What would happen if someone were to take a left-hand turn? Well, you would say in the car, there's something pushing you towards, how do you say this? There's something pushing you into the door. Yeah? Do you understand? Okay. When Jimmy is in the car, and the car is taking an abrupt turn to the right, Jimmy thinks, hey, what is pushing me into the door? Because the door is pushing on me. What is that? Well, what it is inertia. Your natural motion from Newton's first law of motion is to move how? You will go in a straight line unless acted on by an outside force. When you're seated on that oh-so-slick vinyl bench seat, the thing that keeps you from going out of the car is the door. So the door contact force pushes you towards the center. It's a contact force which provides the centripetal acceleration towards the center. Why do you perceive that there's something pushing you into the door? It's because you are in a non-inertial frame of reference. You are accelerating in the car. The car is accelerating, you're in the car, you're accelerating. And we said that physics doesn't work in accelerated reference frames. Okay? There's a nice little trick though, if you ever want to look at it again, is fictitious is equal to minus ma. So when the astronauts are on top of the rocket and it boom blasts off, I don't know if you've seen the movie. I haven't seen it yet, but the Armstrong movie is supposed to be pretty good. The astronauts are sitting in custom-made chairs. Why? Because there'll be a large force acting on them, not at takeoff. It's not a huge acceleration, but later, and they will perceive that something is pushing them down into their chair. Why? Because the acceleration is up. Because they're accelerating, they think there's a force pushing them down into the chair. Apparently, that gets really nasty for the second stage. You've jettisoned the first stage, all its metal, all of its engines, all of its fuel have been consumed. Now you have a much smaller rocket with just a fewer number of engines. And when that baby lights up, you get slammed into your chair the hardest, they say. So when that, you get stage separation, you're kind of coasting along. The astronauts are going, oh my God, this is going to hurt. This is going to hurt. Bam! And they get that second acceleration. Okay? Cool. Let's deal with one more case. Here is an old-fashioned washing machine. Yeah? And I'm going to put some dirty socks and other things in the the clothes washer. Okay? Maybe I've got some purple shorts or something, and I put them in there. And the washing machine generally does what? It gets them wet. Soap, rinse, right? But if I take the clothes out now, due to surface tension between the fabric and the water, it's going to stay pretty wet. And that's not what I want to wear. I don't want to wear wet clothes. Okay? In the olden days, when Granny wanted to dry the clothes before she hung them out on the clothesline, let me just tell you, clothes do not smell as good as they when they're dried on a clothesline. You can't get that with fake odorants. Really awesome. But what she would do is she would take the clothes and she'd have a handle here, and she'd turn the handle, and that would pull the clothes between two rollers that were tightly bound to each other with a spring. So it took a lot of force to make them separate. And as the clothes came out, they had been squeezed between the two rollers and had lost a lot of the water. Okay. How does your washing machine do it? Circular motion. Your washing machine uses circular motion. Your washing machine tub is actually a tub within a tub. There's an external tub that is solid, it's a can, essentially. The inner tub is a can, but it's got holes in the bottom. Why are there holes in the bottom? Water drains. But not only are there holes in the bottom, there are holes in the sides. So if we look at my little shorts here, dang it, my little shorts here, and they are being swept around a center as the tub is called the spin cycle. Yeah? Can my shorts fit through these holes? No, the holes are not that big, right? So what makes the shorts go in a circle? What creates the force? The normal force, the sides of the tub pushing on my clothes. But what about my water in my clothes? The only thing holding the water in place is surface tension between it and the fabric. So if I spin this tub fast enough, the water cannot be supported by tension, and so did that one kind of wrong. It sort of does this. It slips out of the holes on the side. So your washing machine does what? Your washing machine on the spin cycle doesn't go whee. Your washing machine goes what? Wonka, 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 wonka. It comes up slowly because at the beginning there's a heck of a lot of water. So you don't have to go very fast to get some of it out. But you eventually bring it up to a very high speed rotation rate to try to get as much water removed. A dog does the same thing. If you've ever given a bath to a dog, you know this. Because after you give a bath to the dog is wet. Dogs don't like to be wet. And so the dog will throw its body, twist its body in one direction. And surface tension is not great enough for the water to stay on the fur. That is to provide the centripetal acceleration. And so the water comes off of the fur. It comes off in a nice, heavy flow of droplets. So if you're next to a dog that's wet, you're liable to get soaked. Now, why doesn't the dog roll over? Because the dog rotates the front and back of its body in opposite directions. You got some really nice YouTube videos if you look them up there. Amazing to see this dog, and the water just coming off of it. So there you go. More applications than you knew you could have. How about a vertical circle? A vertical circle is no different than any other motion. F equals ma. Please be aware that the centripetal acceleration is always directed what? Towards the center. So in order to solve the question of like, what is the force between the child and the seat? The child rests upon the seat. So which way is the normal force going? This is not a very quick Ferris wheel. The normal force pushes the child up. The speed is to the right. What do I have down? F sub g. And where's my acceleration? Towards the center. Centripetal acceleration. If I'm rotating the Ferris wheel at a constant rate, which is generally what I'll do because the Ferris wheel has load all the way around it, right? I don't want one person to go really quick over the top and then someone else go really slow, okay? And so we get the lovely relationship. Plus F sub n minus F sub g is minus ma sub c if we take up to be positive. So it's F sub n is your weight minus mv squared over r. So your normal force becomes less than your weight. So you feel like you're coming out of your seat. Not exactly so, but you can go so it's noticeable. Yes? Radius. That thing right there. And why is it confusing? Because what should we always put on our diagrams? Center. Yep. One letter makes everything clear. Yeah. So at the top of the Ferris wheel, you feel less contact than you're used to. What about the bottom? There's the F sub n, F sub g. Which way is the acceleration? Which way is the acceleration? It's up, because that's where the center is now. So there I get, again, taking positive to be up, I get plus F sub n minus F sub g is positive ma sub c. So F sub n equals F sub g, weight, plus ma sub c. So at the bottom, you feel a sensation, you perceive that you are heavier than you normally are. Yeah, you're adding to the weight. And this is not only fun on the Ferris wheel, but it's very exciting for roller coasters. Think about roller coasters. They tend to be made of tracks that are curved. And sometimes they're vertical, sometimes they're horizontal, and sometimes they're a mix of the two. There's a screw-type shape. Yeah? So guess what? It's pretty tough to have an inverted roller coaster, isn't it? It's pretty tough to require a force as large as your gravity. That is, it's pretty tough to have F sub n equals F sub g minus mv squared over r. Okay, now this is where F sub n is going down. You're in your seat and you are inverted for a roller coaster. Yes? F sub n is normal force. Well, yeah, that's their symbol for normal force. I hate it. Okay. So here we have what? I guess minus f sub n is that. Wouldn't it have been nice if I'd started out with, I always tell you to start out with. So I have minus f sub n minus f sub g is minus mv squared over r. Here's r. What is the slowest speed that you can go in a roller coaster without leaving the track? Slowest says f sub n goes to 0. A normal force can only push away. It can't pull. So the normal force can go to 0. Yeah? And that's when gravity alone is making something go in a circle. So the part of the path of a parabola, for example, has a radius of curvature, like you're traveling along a circle briefly. So this is called the minimum speed. The criterion would be exactly the same for a ball on a string, where I have the tension. What's the smallest tension I can have? Smallest tension I can have is 0. Tension. Where at the top, what is gravity doing right there? What is gravity doing at the top? Making it go in the circular path. That's the minimum speed. Y'all see that? So we get, in this case, or for a string, that we get f sub g, mg is mv squared over r. So v min equals the square root of gr. So that's where you feel as though you're coming out of your seat. So v min is the square root of gr. So is it easier to go around vertical tracks that have a large radius of curvature or a smaller radius of curvature? What would be more safe? Well, let's look. V min goes proportional to the radius. So if I had a larger radius, I'd have to have a larger speed. Makes me a little bit nervous. You had a question?
So V min equals square root of GR. So what is V equals square root of static GR?
That would be a horizontal track. What's the minimum or maximum speed? Let's go look. Let's go back and look right here. That one. That's the maximum speed to go around a horizontal circle. Good observation. Very nice. Well, let's assume something was going at the minimum speed over the top and the speed was constant. If that were the case, then at the bottom, what would I get? I would get f sub n equals mg plus mac would be what? Whoops. Let me just find it to be ma sub c is mv squared over r. Whoops, excuse me. That's nice. Sorry about that. Okay. Did it go down? Okay. Sorry about that. So we would get, I think, mg. So at the bottom, you feel twice as heavy as you do at the top. So suppose you want to make a roller coaster and you realize that as roller coasters go up, their speed decreases. We'll learn about that with energy, but essentially gravity is opposite to the motion. So you're getting a deceleration, quote unquote, decreasing speed. Well, how can you make your lawyer's happy. Well, the minimum speed that we just found does what? Your minimum speed somewhere is the square root of GR. So if you look at most inverted roller coasters now, the track will come up with a big radius of curvature, but the radius will get small at the top. So that sets a smaller value of velocity at the top. And then as you leave, you go back into a bigger radius. Because if you had a small radius, if you went over like this, you'd probably have your eyeballs ripped from your head if you look down. So we don't want that, right? Anywho, so you can see these type of, we wouldn't call them elliptical, but loop-de-loop tracks now for inverted travel. There you go. Vertical circle, horizontal circle, bank tracks. Circular motion, conical pendulum. What did we introduce? Nothing. We just went over what we went over earlier. Centripetal acceleration is v squared over r. And we examined some common cases of interest. Okay, again, non-uniform circular motion. We've talked about that. Okay, there's that. Centrifugal force, scoliosis, linear systems, whatever. Don't worry about drag forces. Don't worry about speed. Blah-de-bum-bum-bum. That's kind of sad. Okay, I want to die. Coffee filters. Again, things we won't do. I'm sorry. But think about this case. Here's the Earth. Here is the space station. The idea for the space station to stay in orbit is such that the force of gravity provides a centripetal acceleration. F sub big G, because we're no longer on the surface of the Earth, equals m a sub c, so it's m v squared over r. So that's how you determine the orbital speed as a function of radius. And so essentially what happens is the space station is in a parabolic orbit. Yeah, it's falling. But because the Earth is round, it keeps missing the Earth. It's falling at the same rate the Earth is curving away from it. Newton had a lovely way of describing this. Newton said, if this is the Earth, if this is the Earth and I had a cannon and I put it on the top of a mountain and I fired it, I know that the cannonball would fall to the Earth. But let me make the cannon even more powerful. What will the cannonball do? It will go further. But because the Earth is curved, that plays into things as well. So Newton said, what if I fire it just big enough at a speed such that it falls, but it keeps along the curvature of the Earth? Now I've got a satellite, what we call a satellite, or a moon. Planets around a star all follow this. So we'll do universal gravitation in a couple of weeks, briefly. This will be an application. Okay? Yum, yum? Yes? It would be a crispy critter. We can do that. Okay, let's do that. Right now. What is the force acting on you? Gravity. Okay, there's that. At the right speed, you're no longer making contact with the Earth. You're just above the Earth. And we want to find what that V is. Well, let's take that to be positive. So we have F equals ma. And I have plus mg equals ma sub c. So it's mv squared over r, where r is the radius from the center. Notice that the m's cancel, and so I get what? V is the square root of gr. Ha ha! Just what we found before for the vertical circle. Now, g is what? 9.8. What is r? Radius of the Earth. I don't know what those units are. About 6,000 kilometers, or 6 times 10 to the 6 meters. Is that about right? So you multiply that by 10 and take the square root. So it's going to be roughly 10 cubed. And the square root of 60 is about 8. Yeah? Does that work out in the calculator about the same? So you're moving at 8 kilometers per second. That's about what, 5 miles per second? So 8 kilometers per second would be approximately Mach 20. You'd be glowing like a cherry. Yeah, but I think we'd have to worry about aerodynamics at that point. Yeah, but that's an excellent point, because what is one of the big issues for deorbiting, that is, coming into the Earth's atmosphere for a satellite or a capsule, a return trip capsule? Yeah, you're moving fast, right? So you have to slow, you have to decrease your speed, and they use air drag. Now, up in the upper parts of the atmosphere, the air is pretty thin. You'll still start glowing. But as you descend in the atmosphere, the air gets denser and denser and denser. Your drag gets larger and larger and larger. So your terminal speed gets what? Smaller and smaller and smaller. So you have to get rid of the energy, which you do by thermal means. And that's why meteor showers are generally what? Are they big rocks going through our atmosphere and burning up? You see a meteor shoot,